Hello everyone, it's November the 20th. I am slacking today. Oh my god, slacking so much. I also been waiting for my bike, but it's still being delayed. So I don't know. I'll be lazy today. But anyway, pick myself up right now and let's do this. Single element in a sorted array. Doesn't sound like something I've done before. Alright, let's take a look. Have I done this? Nope. Only integers in a sorted array. Every element appears exactly twice, except for one element which appears exactly once. Return the single element that appears only once. Your solution must run in O log n time and O1 space. I mean, we do remember using exclusive OR. Like we can run this in O n time, right? So let me just do this. What was that? An exclusive OR everything. I think we can use reduce. Right? We can use reduce. Reduce when I'm passing a lambda, x and y, right? And x exclusive on y. And I'm passing in nums. I'm gonna return this. Is that a thing? Yeah, I think exclusive OR is the solution. But that is in ON, right? That is in ON, which is not what we want. So we're gonna try to do it on O log n. But definitely we have sorted, so this seems to be binary search, right? So with binary search, okay, binary search for what? So we have the minimum, we have the maximum. So we pick the minimum and the maximum, we go to the center, right? When we go to the center, we can binary search for the index, and we're gonna look, right? So we're gonna look, so whenever we find one, we're gonna look to the left and look to the right. What if we find it's the same? Where do we go? Do we go left or do we go right? That is a good question. We don't know if we should go left or go right, because we simply don't know. Like this one is on the left. It's sorted, yes. And how do we do binary search for this? We don't know, right? How? One element appears exactly once, and everybody appears twice. And then we can locate it in log n time. Interesting. So I have no clue. Because I don't know which side to go to. Like, let's say if I find in the middle, which is will be, it's not really, it will be in the middle. It's already sorted, right? So if we go to the middle, okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I go to the fourth one, 1, 2, 3, 4, 5, right? Fifth one. Right, so I go to the fifth one, we have 4 on this side, 5 on this side. And then what? And then I look to the right. Well, I look to the right, and I look to the left. Ah, I think I got it. Because everything repeated twice, right? So whatever value I'm going to look for, it's going to be look for in the middle, right? So when I divide it in half, if it's odd numbers, and I pick a value, right? So the left and right both will be even number. And I check on my left. If the left is the same, so I have this is the same. So on the left side we have 3. On the right side we have 4, right? Because the total number will be always odd, right? And it's impossible, right? So the single value will only appear. It will only appear if that side is an odd number. Yes, yes. So we go find the middle, right? We go find the middle, and then we find the left and right, and then we pick out whatever the double, and then we count on the side. So we pick out the middle double, duplicate, right? So the middle duplicate will determine where, because the total number is odd, right? So we pick the middle, then both will be even number. But then we're going to look to the left and right of the middle, and then we're going to look left and right, whichever side that has the value, duplicates, then that side will turn into odd. Then we go in that side. So here, the middle one is 3, right? So we look left and right, and we find its duplicates on the left side, right? So the left side will become odd, and the right side will become even. So we go to the left side. The left side now becomes 1, left and right. So left side. So it's gonna be left side. Oh wait, we have to do the math, right? We have to do the math. The left side now, left side is 0, right side is 1. So we go to the right side. So I pick up here. Then we need to go left and right. That is the 1. Yes, binary search. Binary search will do us good. And of course, we already solved it, so it doesn't really matter. So, okay, binary search. We're gonna go low, high. Right, -1. And while low smaller than high, mid equals mi. Mid equals low plus high divided by 2. All right, perfect. Now, low plus high divided by 2 will give us this value. So we'll go left and right, right? We're gonna say if mid -1, if nums, I can go, it's fine, right? Mid -1 is not equal to nums mid, and nums mid not equal to nums mid plus 1. That is the value we need to return. So we just return nums mi. We found it. Right? Or let me see. Or what? Or so we're always gonna go for the odd side. So yeah, this should be good. So if nums, right, mid -1 is equal to nums mid, right? Mid -1, these two are the same. Then we need to find out which side is the even side, right? So how do we find out which side is the even side? Then we will always go to find. So we need to check on the left and on the right, right? So we're gonna say if that's the case, then if high minus mid, right? High minus mid. The mid of not high minus mid. Let's see, high minus mid, right? So high minus mid. Yes, that's the total number of values on the right side. So this one is 0, 1, 2, 3, 4, 5, 6, 7, 8. So it will be 8 minus 4. That's on the right side, right? So if this if this one mod 2 is equal to 1, then we're going to go that side, right? We're going to go that side. How do we go that side? We are going to go that side by setting a low equal to, maybe in this case I should go low smaller than high. So low will be equal to mid plus 1, else high will equal to mid minus 1, right? High, okay, that's not minus 1, it's high minus 2, because mid is equal to mid minus 1, so we're going to have high going to be mid minus 1 minus 2, right? So that's that. Else if nums mid is equal to nums mid plus 1, right? If that's the case, then we say if mid, that's the number of values on the left side. If that is odd, then we say high equals mid minus 1, else we say low will equal to mid plus 1 plus 1, so mid plus 2, right? And we'll always converge in this, so we don't have to return anything. But just in case, we're going to return nums low. But in that case, we probably don't need to do this. Maybe we don't have to do this. If it's equal, else, if it's equal, and then let me see. Right, so they will equal to minus 1, and then low will equal to mid plus 1. Where's mid plus 1? So yeah, I think it should be fine. So we do this. We don't have to do this. Basically do these two, and then we'll return mid low. Okay. All right, we have 2 test cases to run. First one shall return 2. Second one shall return 10. All right. And this will be nums, and here is single nums. Yep, that is exactly what I'd expect. All right, when I run this, I also say this is a what? This is a binary search satisfying, right? Satisfying O log n time and O1 space. All right, let's try this. Do you want to? Yes, I do. Like that. Oh, it immediately goes out. Yeah, that's true. All right, submit this. Oh, we might have an issue. I think there is some problem. When it's in the center, yeah, I realized. Oh shoot. When it's in the center, one is in the center, so we have to go else. Else we just, that means if it's equal to this, we do this. If it's equal to that, so it's not equal to this, yeah, that's just gonna return nums mid. Sorry, I forgot about this case. 1, 1, 2, 3, 3. That should return 2. That's such a basic test case. I feel criminal, right? It's criminal that I forgot about this. this one shall be good. All right, come on. There you go. That is the one. 540. 540. That's pretty smooth. I think we did this one pretty smoothly. 3 simple approaches. Brute force. Caution. What? Reducing. Exclusive OR. Research. Yep. Why do you use mid? Oh. Well, that's true. You can use mid to decide. Duplicate found, and if mid, because if so mid is here, so it has to be, if it's even, then must be on the right side. If it's even, then hold on. Num's mid. Oh wait, hold on. It's 0 based. So if it's 0 based, and in this case, if mid is an even value, and that is the second one, then it must be on the oh wait, hold on. If it's even value, it must be on the left side. If it's even value, it must be on the left side. If it's odd value, it must be on the right side. Exactly. So that was good. What is this? No, this is the same. It's readability. This is the same idea, right? It's the same idea. And we're already using it. It's just we use a slightly different here. But yeah, we got this. All right. Let's roll another one. Yeah, solved in like 15 minutes. Let's go for another one. The forever wait. Huh. Oh, Manchester United lost today, 1-4. Jeez, if Ole Gunnar Solskjaer still kept the job, people are gonna have a riot. All right, this is just horrifying. It's just horrifying, and it's in a game where the head has saved 2, but actually not really 2 penalties. It's 1 penalty taken twice. So he saved the penalty. In a game where he saved a penalty, they lost 1-4. And they got Harry Maguire red carded. Jeez, that dude is celebrating goals against, like, in the World Cup, England's World Cup qualifying. Is like, oh, I'm such a hero. I think he scored 2 games in a row. I'm back into the Premier League. Laughing stock. Unbelievable. All right, let's take a look at this. Minimum size subarray sum. Given an array of positive integers and a positive integer target, return the minimum length of a contiguous subarray of such the sum is greater than or equal to target. If there's no such a subarray, return 0 instead. So in the return the minimum length, okay, so 7, the minimum length is going to be 2 because 4, 3 is 7, right? 4, minimum length is 1, we take 1. If it's 11, it's nothing. If you have figured out the ON solution, try and code on... Wait, did I read it right? If you have figured out the ON solution, try coding another solution for which the time complexity is O n log n. If I already found O n, why do I need O n log n? It doesn't make any sense. But anyway, this one screams dynamic programming, which I think must be some sort of modification of Cadane's algorithm, of which I already forgot. I mean, the good thing is you don't really need to memorize all these algorithms. That's not the point. The point is to know how to approach these problems so you can always start from fresh. Right? That's always the beauty of math, right? You know some tricks, but eventually it's all about understanding. Man, I'm having problem with my sensors. This cat lose the internet. Right, anyway, so what we want is the minimum length of a contiguous subarray with the sum larger or equal to the target. I can do prefix sum, and after doing prefix sum, let's try a prefix sum. So 2, 3, 1, 2, 4, 3. So it'll be going to be 2, right? And 5, which is still smaller than 7. 6, still smaller than 7. Now we're going to be 8, right? So 8 is the first time that we are bigger than 7. So what do? Well, we want to find if there's any subarray that ending at 2 that can have a target value larger or equal to 7. Now I'm at 8, right? So I need to find if there's any subarray sum so far that can take 1. So I can do a binary search because it's all sorted. So I do a binary search to find 1, and this one results in nothing. We don't find anything, right? Binary search say there's no 1, and the smallest, well, it cannot be smaller, it has to be larger than 1. So we can do bisect right? Bisect right. And when I do bisect right, what I need is to compare the value that's going to insert. I'm going to insert at position 0, right? So whichever position I'm going to insert, that position is going to be the current value that's larger than it, right? The current value that's larger than it. So I check for 0 and check for 2, and then the result is 6. Is no good. So which means currently with 8, our number is 1, 2, 3, 4. Is 4, right? Next one is 4. We got 12, right? So we only got 12. To get to 7, we need 5, right? So we need 5 to get to 7, and what we find is, oh, we have 5. So we found 5. So that just means for this minus this. So we have 3. Now we have 3, right? Now we have 6, 8. That's like 1, 2, 4, right? So that's 3. Last one is 3 is 15. So 15 to get to 7, we need 8. And we do find 8. And the result is 2. So that is O1 log n. Because I check every single value, and at every value, I'll do a binary search of the previous one to find out the current smallest value that is larger. No, I'm going to do it again. The current, because I'm going to need to minus something, right? So I need to minus I cannot minus bigger, so big is small. So the minus, so the largest value I can minus, right, from the current prefix sum that make my target larger or equal to 7. And when I find that, then I get the range. And I just keep going to find the range. Yeah, so I'm going to minus this, and hold on. I need to minus this value to be larger or equal to. Is it actually going? No, I have to bisect left. Because I need to get something smaller. I cannot get something bigger, right? So like, if I when I start and I reach here, which gives me currently, yeah, I think, yeah, which this one will give me 8. right? This one gives me 8, and I need 1, right? I need 1 to get a 7 or 0. So I need to find something, I need to find in the previous that's smaller or equal to 1. So it's going to be bisect left, right? Bisect left. And I'm going to check the value bisect left. And if the value is larger than 1, then there's no go. That's actually because, well, hold on. I can add a 0 to the front. I can add a 0 to the front to make the whole thing easier. But anyway, so like here, we have 8, right? We need to find 1. So the prefix sum needs to be 1 or smaller than 1. I mean, binary such. And this tells me I need to put in 0, right? So I check for 0, and there's nothing, right? So 0 is the first value. So, which is no good, right? Which is no good. But if we do find a match, okay, if we do find a match, how do we check if we find a match? Well, then we always do wait, what's the rule if we have duplicates? I think it's always go to the bisect left or bisect right. So it will insert in a certain position, right? And then always insert at a certain position. So we insert here. So I always do that position, -1. And if it's smaller than, if it's 0, that means there's no match. Right? There's no match. So no match for 1 or smaller, right? So that means what I have is what I got, right? So this one is 4. Right? At this position, it's 4. Because what I find is position 0, which is fine. Yeah, position 0, I just -0, right? And in here, because if I go to the left, if I match and I go to the left, right, I'm going to bisect left, and that is exactly the position I need to minus. Yeah, that's exactly the position. Right? So 15 requires 8. Now we find 8. And if I bisect left, it will go to the left. No, we're not bisect right. And we will bisect right. We bisect right, and then we're going to check for the left. So whatever position they give me, then we check for left. And if left exists, then we're going to do, if left does not exist. Okay, so how about this one? This one will always be, no, this one never reach 11, so this is always going to be 0. Okay, so I actually have on log n, right? Believe it or not, I have on log n, but I do not have on. I think this is wrong. It's like if you figure out on log n, try to see if you can do it on. I mean, that's what it is. Doesn't matter. Let's do the on log n first. Now this is not Cardane. What do we consider this as Cardane? Is this even dynamic programming? Not sure. Anyway, so we need bisect. So from bisect, import bisect. I'm going to do right. It's always going to be right. Right? So what I'm going to say is pre-sum. Right? Pre-sum will equal to list, all the way to accumulate from iter-tools. Import. Ooh. Yeah, that's fine. That's fine. So we're going to just accumulate right, nums. And then we're going to say for s in presum, for I s in enumerate, right, presum, what we're going to do? For I s in enumerate presum, and we just say if, right, s is larger or equal to target, all right, then we're going to say index equals bisect right. Actually, I don't know. Do we put the value first or do we put? Jeez, I don't know. Don't remember. From bisect, import bisect right. So bisect right. Param a, the param x. I don't know. What does a mean? A is this. X is this. No, that's wrong. Oh yeah, it is. So the presum goes in first, and the value goes in second. So the value will be s minus target. Now we get an index, and we say in the result. So res equals to 0, right? No, res will equal to len target. Then we say going to be the current index minus index minus 1, right? That will be, let me think. If I'm here, to 3 minus this, right? So 3 minus this. Yes, so going to be index minus 1, but I need a max value of this and 0. So res will equal to max res and this. No, not max. Come on, min. Then we return res at the end. Okay, let's try this one. So this will be, this 7 will be 2. 144. 144 is what? 4 will be 1. The last one is all 1. That will be 0. Okay, okie dokie. So target, nums, min, nums, no wait, target first. Target nums. Int is not iterable. Oh shoot. My bad. Just the target goes first. Target goes first. I have no idea what happened there. I am so sorry. Okay. Oh my. Ha! What do I do now? Cannot be math. Alright, from math, I just import math. The easiest. Math.inf, right? Return res. Return the minimum. Hold on. What do we do? Return. Yeah, the minimum between res and len nums. No, that will become no. What I'm thinking, that's not right. Return res. return 0, right? If res equal to math.inf, I also return res. This one shall work. Try it. Wrong answer. Jeez. Alright. What the hell? You 1, 2, 3, 4, 5. It'd be 5. What do I have? I have 4. Huh. Why? Well, up until here, so it'll be 0, 1, 2, 3, 4. If it's larger, then it will be minus. Holy guacamole. So in that case, I was wrong. It has to be index minus 1. It has to be index minus 1. So minus index plus 1. It has to be. Yeah, that's how you get, yeah, that's true. Index is smaller. Well, in that case, yep, no complaint. I got this logic wrong. Yeah. I think maybe it's because I'm moving a little bit too fast than my desired pace. There we go. How we got it. So this is so use prefix sum and binary search at each step. Binary search at each step, trying to find where is the minimum possible. Where is the minimum possible subarray to reach a range sum that is. Hold on, I lost my internet. Come on, get back. There we go. All right, so we say to reach a range sum that is larger, right? Larger or equal to target. So this one will run O(n) log n, and we hit a 72 milliseconds, right? 72 and 78%. Okay, so can we figure out an O(n) solution? I think that's what it's asked for. Unless it's not what it means. We can do O(n). How do we do O(n)? I might have an idea, but I need to try it out. So no, actually I don't have an idea. I mean, O(n), instead of binary search, we can do, let's say, a hash map, right? Let's say I need 1, and I look into the hash map, and it does not exist. Then how do I know? Because I can be anything smaller than 1, right? If I need 1, if I need any value, I can pick anything. I can pick the largest that's smaller than me. That's what it is. The largest that's smaller than me. How do I know which one is the largest or smaller than me? Two. All right, I don't want to think. Let's see. No binary search. Brute force definitely is not going to work. A better brute force. Binary search. That's O and log n. Yeah. We can actually just try to see a hint, right? We're not really going to copy exactly, but we can take a hint. Oh, come on. I didn't do anything. I just... Is it dead on me again? Unbelievable. There we go. Using 2 pointers. All right, I only read that. Using 2 pointers. Is that ON? What do you mean using 2 pointers? Left and right? No, I think it's all starting from the front. Oh, it's like sliding window. Hold on. Left and right. Oh, yeah, sliding window. So we have a slow and we have a fast. So left and right, right? Low and high. So high keeps moving until we find one that is larger than the target, and then we compare it to the low, right? And then if the low is smaller, while low is smaller than, while low is smaller than the target, then what's needed, then the low move forward. So move forward until low is not smaller than. Well, actually, low move until low is not smaller or equal to, right? And then we're gonna do this minus that. Keep moving. Yes, so thank you very much. I do think it is possible. And actually, the beginning will be the same. These will be the same. So that is going to be a O and log n, not ON. So sliding window. 2 pointer, a better term is sliding window for ON. So everything the same. We have low, high. One is 0, 0, right? So for the high is just going to be for, actually, we just need a low. High can be for high in. We can actually do for high s in enumerate Prefix Sum, right? And then we say if high is larger equal to target, then we say while Prefix Sum low is smaller equal to target, no, s minus target, then low plus equal 1. Right, once we're done, res equals to min, res high minus, pay attention to what you minus, high and a minus, because low already plus equal 1, right? So high definitely minus low. Let's see, 3, 4, 5. 5 minus 4 equal to 3, 4, 5. 5 minus 3. So yes, that's it. And then we're gonna return res. So while, hold on, while this is smaller, so it also has to be low needs to be smaller equal to s, and not smaller equal to s, not equal to high. Can now go above high, and this is smaller to that. And then we keep going, and then we're gonna try this sliding window approach. Res equals infinity. All right, something is not right. Oh, because high. That's s. We need a plus 1 as well. What? Why? Low smaller equal to high, and pre-sum low is smaller or equal to s minus target, low plus equal to 1, and they're equal or we're not. So they're going to keep going until it's not, right? Now I'm going to do that minus that. Oh, yes, for sure we have the plus 1. I have no clue why I did not plus 1 earlier. I do have the plus 1, and we cannot return res because we have to return 0 if res equal to math.inf else res. Okay, so this is on, sliding window on. All right, we'll try this one. Yep, I think this is sliding window. I think this is what it's asking for. On, right? So, in that case, but we still need it, right? Wait, are we not recording? Oh, we're changing the num directly. I'm not sure if I like that idea, but doesn't matter. So I'll sum larger than this, and so you get minimum this. So we'll go one by one, but it's the same idea, right? It's the same idea. We have the current sum, the larger equal to this, and but where do we change num? I don't see you change num. We just have a sum. Keep incrementing. Yeah. While sum larger than s, and the answer equals to the minimum of answer. I plus 1 minus left. And sum minus equal. Oh, I was wrong. You don't have to use prefix sum. We just adding everything up, and if it's larger, then I start at minus. Oh, it's even better. Oh, wow. Yeah, I think I got stuck in the prefix sum mindset. I didn't realize this is possible. Brilliant, brilliant. So this is from Better Sliding Window, from the official solution. Definitely. Well, this one's much better. There is no need to create a prefix sum. You simply use one variable to accumulate the sum, right? Once the sum is larger or equal to target, we simply deduct the numbers from the start until we reach a subarray whose whose range sum, right? That's what we have. Whose range sum is larger or equal. Well, until we reach the subarray sum whose range is smaller. Actually, it's smaller than target. And then we know, right? And then we know the smallest possible range to have range sum larger or equal to target. Yeah, this is much better. Much better. So still, it's going to be on space, on time, but o1 space. Right. Well, this is still on time, and this is on space, which is not really necessary. All right, so let's write it from scratch. How do we do this? Well, we have a low, we have a res, right? What else do I have? For high, s, no, s, n, and enumerate nums. Oh, we also need a p sum. Okay, we need a p sum as well. All right, so we say p sum plus equal to n if p sum is larger. Actually, it's going to be while p sum is larger or equal to target. Then we're going to minus, right? And p sum minus equal to nums low, right? Actually, if it's larger or equal to, we should probably do it immediately, right? So larger or equal to, then I check, right? Coming back and check. So I should check every single time. I think I should rest will equal to the minimum rest and high minus low, right? Low, I start from the beginning and it has to be +1. So rest equal to this, and then with the minus low, and the low plus equal 1. All right. So when p sum is larger than target, then I'm gonna record the rest and remove the current low, move the low forward, and try again. If it is still larger than target, I record the rest again, remove it. All right, remove this low, keep going, and then because I remove it, I remove the current low, the low move forward, right? And now this value is smaller, then I don't do it anymore. So I go out. This same thing, return, res, 0, if res, I actually be cheeky, times res is not equal to math.in. Uh-oh. How about we int it? Uh-oh. Ain't gonna work. I thought it was gonna work. Alright, so 0 if res equals to math. Inf else res. Yeah, this is a better, much better. Alright, try this. I don't think we'll change the runtime, but it's definitely better. Alright. Well, that should be it. We got 2. And actually both went pretty smoothly. Both went pretty smooth. Not very difficult, I think. I mean, a little bit summarizing. The first one we can solve easily in ON using exclusive OR, but with binary search, we can go for O log n. Yeah, that's good. The second one we solved in O and log n start, and then we saw the hint, right, to use 2 pointers. So we have our version of ON, but ON space, and then finally realizing we don't need to have a prefix sum. We can just keep adding and keep deducting from the solution. So yeah, this is actually a good interview question. Have different levels, right? I like this question. I didn't like the other one. This is a good interview question. All right, that will be it for today. I'll see you guys tomorrow. Adios.